Hello guys, welcome on Tesla Adventures. In this video, we are going to discuss the detailed analysis of thermal expansion. We are going to discuss the isotropic and anisotropic solids and linear, volumetric and superficial expansions. And first of all, let us discuss the real cause of thermal expansion. We all know that each atom, each solid is formed of a crystalline structure in which atoms are arranged at specific points which are called as lattice points. And those atoms are not at complete rest, in fact, they are vibrating. They have vibrational energy and they are vibrating. So I am representing this lattice structure with springs. I am assuming that these atoms are placed at lattice points and they are connected by this spring, because spring shows the fact that they would vibrate. So we know that vibration is a kind of small vibration is a kind of SHM. And if we are watching any solid, for example, you are watching a pen, then you are watching a specific fixed length of that pen. Okay, so what is that length? So if you imagine that pen is formed of many atoms which are vibrating about their mean positions. So we know that in SHM the average displacement is 0. So if we seize all the atoms and if we fix them on their mean positions respectively, then the length formed of the pen will be the length which you are watching in front of you, which is the length of the pen. So this is average length. So let us analyze the vibration of any two atoms, which is a pair of atom, and let us see that what happens to the potential energy. We all know that interatomic potential energy curve with the interatomic distance x is like that, and it is a asymmetrical curve. The reason behind the fact that I am telling that it is a asymmetrical curve is due to the shape you can see in the figure. So if it would have been symmetrical, it would have like this, like a parabola. But it is asymmetrical curve, and this asymmetrical curve is the real reason behind the thermal expansion, or we can say that this asymmetricity is the real reason of the thermal expansion. Now let us discuss that at a certain temperature T1, let us mark this temperature as T1. This is a temperature T1. The potential energy of this pair of atom is minus U1. And this is the minimum separation between them because they are vibrating. So there would be a time when they would be at minimum separation like that, R minimum, and there would be a time when they would at maximum separation from each other. This is R maximum. So this is R minimum, and this separation is R maximum. Okay, so let us name it R maximum 1. Now if we increase, now we know that the average of these two is somewhere in this at this point, R average 1. Now if we increase the temperature, then this is the temperature T2. Then at T2 the potential energy of this system increases, and you know that obviously this potential energy is negative. So increased potential energy would be less negative. So the magnitude of this potential energy would be less negative, and hence it would be above this line at this point. So this is minus U2. Let us suppose that this is minus U2. this one. So at temperature T2 you can see that this R minimum shifts in the backward direction, which means that the minimum distance between these two atoms decreases, because obviously the kinetic energy of SHM and the potential energy increases due to the increase in all over energy, and therefore their amplitude will increase, and therefore the minimum separation between them will decrease. So this is the new R minimum, so let us name it as R2 minimum, and due to this asymmetric nature, this is the new R maximum, R2 maximum. Now you can easily observe that the change in R max is quite greater than the change in R minimum. So you can see that delta R maximum is very greater than delta R minimum. Therefore, this average R would not remain at the same position. In fact, due to the greater increase in R maximum, this average separation between the atoms would shift towards R maximum, and this is the new average separation of the atoms. Therefore, we can say that all over the average separation between these two atoms has increased, and therefore the length of that pan at higher temperature has increased on the macroscopic level, because we know that on the macroscopic level the average separation between each atom is constituting the total length of the pen. So if the average separation between each atom is increased, then the total length of the pen, which you are watching on the macroscopic level, will be increased, and this is called as thermal expansion. So if this curve would be symmetric like that, then we know that in a symmetric curve like that, for any value of R max, R minimum, the R average would remain at the minimum point. So if this curve would have been symmetric, then there would be no thermal expansion, and therefore we are referring that this asymmetric nature of this potential energy curve is the real cause of thermal expansion. Now let us see that how many kinds of thermal expansions are there. So let us first of all see that the first kind of thermal expansion is linear expansion. And linear expansion does not necessarily means the length. In fact, we can say that the change in any one dimension of the objects is the linear expansion, obviously. And we know that gases and liquids do not have any area and volume, in fact any area or length. Therefore, there is no linear expansion observed in gases and liquids. So linear expansion is only observed in solids, and let us see that what happens here. That you can see now, this is a rod which has some initial length L naught, and let us suppose that initial length is L, and the initial temperature was T naught, and at some higher temperature T, the expanded length is delta L, and therefore the total final length is L plus delta L. So we know that the change, it is experimentally observed that the change in the length due to thermal expansion, small change in length due to thermal expansion, is directly proportional to the original length as well as the change in temperature dt. So when this proportionality sign is removed, then a constant comes which is called as coefficient of linear expansion, which is alpha, and this is dt. So dl upon L is equal to alpha dt, and integrating these two, the limit of L would be from L naught to L, and limit of T would be from T naught to T. Okay, so this is ln L by L naught, and this is alpha T minus T naught. So this is we can say it delta t, and L is equal to L naught alpha, in fact e to the power alpha delta t. So this is the formula for linear expansion. But we know that if alpha is small, then this is a series expansion of exponential in which we would neglect the higher terms. So let us see that if we neglect the higher terms, then e to the power x is equal to 1 plus x. So this is L is equal to L naught 1 plus alpha delta t. So let me remind you that this formula is only valid when alpha is constant with temperature, because we have assumed the alpha as constant in this integration, and alpha is very small because we have neglected the higher terms of this expansion. So this formula is the formula of linear expansion, and this alpha is the coefficient of linear expansion, and the unit of alpha is you can see that unit of alpha is Kelvin inverse and this is coefficient of linear expansion. You can see that this is a square or a rectangular plate whose dimensions are L1 into L2, and if we increase the temperature, both of its dimensions would increase. We are neglecting its width because we are talking about the superficial expansion only here. So let us see that what is the area. So area of this plate would be L1 into L2, and if we differentiate it dA by dt, then it would be dL1 by dt into L2 plus L1 into dL2 by dt. Now this is dA by dt, and this dL1 by dt is alpha L1, because this T is temperature. So let me write it down as capital T, because it would create the confusion that it is time. So it is not time, in fact it is temperature. So let me write it down as capital T. So you know that dL1 by dt, which we have already discussed, that dL by dt is alpha L. So this is alpha L1 and this is L2, and alpha 1 is due to the fact that I am talking about a solid which has different expansion coefficient, linear expansion coefficient in all three directions. So in this case we are referring only two directions. So we are assuming that if this solid expands in this direction, if its length L1 expands, then the coefficient of expansion is alpha 1, and if it expands in this direction, then we can say that L2 expands, and therefore we can say that coefficient of linear expansion is alpha 2. So we would write down dL2 by dt as alpha 2 L2. Okay, so dA by dt is equal to, you can see that it is equal to alpha 1 plus alpha 2 into L1 L2, and this L1 L2 is the area. So dA by dt or dA by A dt is equal to alpha 1 plus alpha 2. So we can also refer it as beta, where beta is the coefficient of superficial expansion, coefficient of areal expansion or superficial expansion. So for those kind of solids which have different expansion coefficients in all three directions, we can say that this is the areal expansion coefficient is beta, and this is alpha 1 plus alpha 2. Now there is a very important thing which we need to discuss, that in this case, if we consider that there is a cube, let us consider a cube which is a three-dimensional structure, and this cube obviously has 6 faces. Okay, so let us see that its length in this is x-axis, this one is x-axis, and this one is x. Let us suppose that it is x, or this is x, and this is y, and z is this one. So let us suppose that this length is Lx, length measured in x, this length is Lz, and this length is Ly. So it is very important to note that there are 6 faces, and each face is in different plane. So beta of that face, which is in xy plane, or it is parallel to xy plane, would be alpha x plus alpha y, where alpha x is the linear expansion coefficient of this solid in x-axis, and alpha y is the linear expansion coefficient of this solid in y-axis. Beta yz would be equal to alpha y plus alpha z, and beta zx will be equal to alpha z plus alpha x. So this is very important to know that as we know that there could be 3 different planes, and therefore there could be 3 different coefficient of superficial expansions. Okay, but for isotropic solids, so isotropic solids are those which have same expansion coefficient in all 3 directions. So alpha x is equal to alpha y is equal to alpha z, and therefore we can say for isotropic solids beta is only 2 alpha, because in any direction if you will calculate, then it would be equal to 2 alpha, where alpha is the linear expansion coefficient in any one of the direction. Okay, and now we come on volumetric expansion. So in this volumetric expansion, you can see that there is a cube which is having different length in all 3 directions, and this is a an isotropic cube in which we know that its expansion coefficient in all 3 directions is different. So this is a cube, and in this cube you can see that volume will be equal to L1 into L2 into L3, and dV by dt will be equal to L1 into d by dt of this L2 L3 plus L2 L3 into d by dt of L1. So you can easily understand that dV by dt would be equal to L1 into dL2 by dt plus L1 into dL3 by dt plus and here would be L3 also, and here would be L2 also, plus L2 L3 into dL1 by dt. Okay, so what we can do, we can write down dL2 by dt as alpha 2 L2. So this is alpha 2 L1 L2 L3. We can write it down as alpha 3 L3. So this is alpha 3 L1 L2 L3, plus we can write it down as alpha 1 L1. So this is alpha 1 L1 L2 L3. Okay, so this dV by dt is equal to alpha 1 plus alpha 2 plus alpha 3, and this is V. V is the volume. So dV by dt will be equal to alpha 1 plus alpha 2 plus alpha 3 into V, and V is here, and we can write it down as gamma, which is the coefficient of volumetric expansion. So gamma is the coefficient of volumetric expansion, and this is equal to sum of the alpha of all three directions. And for isotropic solids, we know that alpha 1 will be equal to alpha 2 will be equal to alpha 3, and let us suppose that it is alpha. So gamma will be equal to 3 alpha for isotropic solids. Now you should always remember the fact that this volumetric expansion is observed in all solid gases and liquids, as we know that obviously gases and liquids have volume, but they do not have any length or area, and this formulae is only valid when these expansion coefficients are constant and very small. I would be discussing some of the questions in which the expansion coefficients would be variable also in the later part, and if they are not small, then what we'll do, we would be discussing with the concept illustration problems. So this was the complete thermal expansion basics, and in the next video we'll be bringing another concept related to the thermal expansion. Thank you.